Hello everybody and welcome to part B of chapter 3.5. We're going to keep on doing this curve sketching following from the notes we took in class today. So we're going to start with an example. We're going to be asked to sketch and analyze the graph of this rational function x squared minus 2x plus 4 all over x minus 2. Alright, we're going to begin the same way we did before. We're going to first look at our intercepts. Let's deal with our x-intercepts first. Remember, we would have to set this equal to 0, so we have x squared minus 2x plus 4 all over x minus 2 equals 0. And it follows that I could multiply both sides by the denominator and make the denominator go away. When I do that, I'll get the equation x squared minus 2x plus 4 equals 0. And what's going to happen here is this trinomial is not going to be factorable, and it's not going to get us real solutions when we run it through the quadratic formula. So what we say is no real solutions. It's going to say no real sol. So in short, we have no x-intercepts. Let's deal with y-intercepts now. Just by looking at it, we can kind of do this one in our heads. Y-intercepts happen when x is 0. So take a second and just kind of eliminate all these x's in your head right now. Basically, we're only looking at the 4 over the negative 2. And we know 4 divided by negative 2 is a negative 2. So when x is 0, y is negative 2. That is our y-intercept. Now let's look at asymptotes. Horizontal asymptotes. Let's discuss this. We can see that the numerator degree is greater than the denominator degree. And normally this means that there aren't any horizontal asymptotes, but like we discussed in class, the numerator degree is greater by exactly 1. 2 is 1 bigger than 1. So what this means is, we're going to first reiterate, this is greater than the denominator by exactly 1. I'm going to underline that so we understand what's going on here. Exactly 1. So what follows is a slant asymptote must exist. Here's how we find slant asymptotes. We perform some long division. I understand this is probably a review skill, so let's review it. To do some long division, I take what's on the bottom, I put it outside, x minus 2, and then I draw that little box over what was on the top, x squared minus 2x plus 4. And now I ask myself, x times what gets me x squared? And the answer is x. X times x is x squared. Now I take this x and I multiply back. So x times x gets me x squared. X times negative 2 gets me negative 2x. Now for anything effective to happen here, I have to change the signs of everything on the bottom. So I get a negative x, positive 2x. And when I do that, what happens is my x squareds cancel and my 2x's cancel. And I get a remainder of 4. So up here I say x is my quotient with a remainder of 4 over what I was dividing by, 4 over x minus 2. And so what this means for the graph of our function is that there's a slant asymptote, just like kind of helps spell it, if you say it out loud, at the quotient, and the quotient was x. We're going to ignore the remainder. We're going to look at just what the quotient was without the remainder. The quotient was x, so we're going to say we have a slant asymptote at y equals x. And so that line is going to be an asymptote for us. Okay, that's horizontal. Now let's talk about vertical, just because this can be done really quickly. Take a look at the bottom of that function, guys. What can x be on the bottom to make it 0? Well, that's pretty easy. 2. 2 minus 2 is 0. So our vertical asymptote is going to happen when x equals 2. All right, moving on. Let's talk about symmetry next. This one is a review that we covered earlier, so I'm going to move kind of quickly through it. Let's test for y-axis symmetry, so let's throw in a negative x everywhere. Negative x squared minus 2 times a negative x plus 4 all over negative x minus 2, and the answer is nope, that's not the same. This is not the exact same equation that we had in the beginning. They are not equivalent, so the answer is no, that's not symmetric there. X-axis symmetry, well, we just make the y negative this time, and we keep everything else the same. And it looks like that again is not an equivalent equation. Not an equivalent equation. Not much more I can say there. Origin, make the y negative and also make the x's negative at the same time. Okay, so what's going to happen here is I'm going to have a negative x minus 2. I'm going to have an x squared plus x plus 4. And what happened is they would be equivalent equations if I could factor out a negative 1 from both sides and then get the same equation I started with. But I can't do that here. My signs don't really match, and it's not going to give me an equivalent equation, so I'm going to say no. All right, that was a little bit useless, but we had to do it. So now we know it's not symmetric. Let's do the interesting stuff. Let's start our first derivative test so we can find out increasing, decreasing, and extrema, the fun stuff. All right. We are going to have to use our quotient rule skills to get the derivative going here. And remember, we got low d high minus high d low. So low x minus 2, derivative of high, which would just be 2x minus 2. I kind of got that part written right here, so derivative of the top would just be 2x and then minus 2. Great. And then I have minus high, which is that whole trinomial, x squared minus 2x plus 4, times the derivative of the low. Well, the derivative of the bottom is just 1, because there's an x there and then a constant, so it would just be 1, and multiplying this by 1 won't change anything, so I'm going to leave it alone. And then I have low squared, x minus 2 squared. If we FOIL this guy out, we get 2x squared minus 2x minus 4x plus 4. I distribute my negative, negative x squared plus 2x minus 4. I put it all over, x minus 2 squared. I combine my like terms, and I cancel where I can, and I get x squared minus 4x all over x minus 2 squared. I'm assuming that this is just kind of a hop, skip, and a jump for you guys. I'm not really thinking that that's too difficult. If you are finding right now in this video that you do not understand how we went from this to this, that is something you should come after school, ask me a question in class about. All right. So we have established that the derivative is this rational function here. And so what we're going to do is we're going to look at this rational function, and we're going to find out what would make it 0, and those will be our critical numbers. So what we first need to do, though, is factor it fully on the top just so we can really see what we're working with. Okay. There we go. So now we have some critical numbers we can work with. We know for the top what's going to make this thing 0 for a critical number for the first factor is just 0. If I set this equal to 0, I would get x equals 0, so there wouldn't be a lot of work done there. My first critical number is going to be 0. And then here, if I set this factor, x minus 4 equals 0, I'd have to add 4 to both sides, and so 4 would be another critical number. On the bottom, remember, we're also interested in what makes this undefined and what makes the bottom 0. So what would make the bottom expression here 0, this factor, would be 2. And so I've arrived at my 3 critical numbers, 0, 2, and 4. We're going to use that number line method. instead of that weird table your book uses. You're welcome to use the table if you like that better, but I kind of doubt you do because it's really confusing looking to me. All right. Now that we have our critical numbers, we can pick some test points that we're going to use. So maybe a good one to use to the left of 0 would be -1, pretty small. 1, 3, and 5. Remember what we're doing with these numbers is we're substituting them into our first derivative here so that we can find out if we're increasing or decreasing, if we're positive or negative. I'm going to go ahead and write out what those are. I am expecting that you're kind of chugging along here in your own calculator and doing that part on your own. We get a positive number when we substitute -1. We get a negative number when we throw in 1. We get a negative number when we throw in 3. And we get a positive number when we throw in 5. And so what this is telling us is exactly how our graph is behaving, right? We're going up and then we go back down. So we have a maximum here at 0. And at 4, we have going down and then going back up. So we have a bottom, we have a minimum. And in order to find out what the y value is, I have to evaluate my original function. So my original function repeats not this, not your derivative, not derivative of 0. Your original function of 0 is -2. And my original function, not the derivative, my original function, my x squared minus 2x plus 4, all over x minus 2, that at 0, or pardon me, 4, is 6. And so what follows from that is that I have a maximum at the point 0, -2, and I have a minimum at the point 4, 6. Pretty cool stuff. That's going to be very useful for us in a second. That's all we're going to get from the first derivative. Now let's go through the second derivative. Second derivative. And we kind of had to go pretty quickly through this part in class, but we are going to go a little bit easier on you right now in the video. Okay. So we're going to find f double prime of x by using that quotient rule once more. So we're going to go low, which is x minus 2 squared, times the derivative of the high. So I'm going to write that out. d dx of the high, of x outside x minus 4. Minus high, which is x outside x minus 4, minus 4, times the derivative of the low, derivative of x minus 2 squared. And we have it all over low squared, so x minus 2 squared is to the 4th. Okay. We can start to find the derivatives here. But I'm going to take a little, time out here, a little, just sort of, what's the term I'm thinking of? Detour, that's the word I'm thinking of. I'm going to take a quick little detour here, and I'm going to show you each of these derivatives separately, and then we're going to throw them back in where they belong. But let's just kind of be clear about what they look like first. So, the derivative, d dx, I'm going to get rid of this equal sign over here. This shouldn't be here. Let's get rid of that. Okay. d dx of x times x minus 4. Well, we're going to use the product rule here. So our f is x, our f prime then is 1. Our g is x minus 4. And our g prime is 1. Great. So first I'm going to do f times g prime. So I'm going to get x. I'm going to say plus f prime times g. And that just means 1 times x minus 1 or x minus 1. I combine my like terms and I get 2x minus 1 as my derivative there. Great. Over here I'm going to have to use the chain rule when I do my derivative, d dx of x minus 2 squared. I'm going to throw that 2 in front, original function to the first power now, and then I say times the derivative of the inside. Well, the derivative of the inside is just 1, so this is actually my whole derivative right here, 2 times x minus 2. Great. Now let's fill those pieces in. Remember, this is where we got this, and right here is why we're talking about this. And we're going to take those and we're going to put them back in to the function where they belong. So we're going to write everything out again. X minus 2 squared, but now we're going to say it's times 2x minus 1, minus our x outside x minus 4 times 2 outside x minus 2. And we're going to put that all over our x minus 2 to the 4th. All right. And now what we're going to get to do is write out these binomials kind of expanded. So we're going to say x minus 2 times x minus 2. And then we're going to say times 2x minus... Oh, just realized I made a mistake. Back here, this is x minus 4, so this needs to be x minus 4, and this needs to be x minus 4, and this needs to be 2x minus 4. So go ahead and make that change in your notes real quick. This should be a 2x minus 4 here, and this should be a 2x minus 4 here. Okay. And now we have minus, and what this whole thing multiplied out is going to be is x outside of x minus 4, and when I distribute this 2 here, that's going to become the binomial 2x minus 4. Okay. And now I've got everything set up nice and neat, and so I can start to combine all of these binomials and start to FOIL and do some fun multiplication. So what I'm going to get when I do x minus 2 times x minus 2 is my x squared minus 4x plus 4. Remember, that's just the expansion of a binomial there. X squared plus twice of the b, or minus, since we have a minus here, minus 2b, and then b squared at the end. And we say that's times 2x minus 4. And then we say minus an x times, this FOILed out is going to be 2x squared minus 12x plus 16. And I put that all over my x minus 2 to the 4th. Alrighty. And I take all of this and I FOIL one last time. And when I do that, when I distribute this 2x and this negative 4 and this x to everything, I get a whole bunch of the following terms. I get 2x cubed minus 8x squared plus 8x minus 4x squared plus 16x minus 16 minus, in parentheses, 2x cubed minus 12x squared plus 16x. Alrighty, all over x minus 2 to the 4th. Alright, we're going to continue this on a page. Let me just move this guy up so I can keep showing you here. Okay. Move that up there like that. Okay, there we go. That's a little bit easier to work with. Let's keep that going. Great. Alright. Move that wire over. Cool. Now, what's going to happen is, first I'm going to distribute that negative, so I'm going to have 2x cubed minus 8x squared plus 8x minus 4x squared plus 16x minus 16 minus 2x cubed plus 12x squared plus 16x all over x minus 2 to the 4th. Now, once you've gone through, you've combined everything and canceled everything that you can on top, you should be left with an 8x minus 16 all over x minus 2 to the 4th. We can factor out that 8, and we get an x minus 2 all over x minus 2 to the 4th. So just like that problem in class, we can cross off an x minus 2 from the bottom, and we get 8 over x minus 2 cubed. And that, ladies and gentlemen, is our second derivative. Oh boy, we've got a lot of work to get there. Alrighty, so here's what we're going to do next. we are going to look at our critical numbers from our second derivative, and then we're going to do the second derivative test. So critical numbers, clearly on the top I can't really make this 0, it's just a constant 8, so that's not going to work. But on the bottom, check it out, I have a critical number 2. 2 would make the bottom of this fraction 0. So I'm going to throw the 2 right here as a critical number, and then I'm going to do my number line, and I'm going to throw a 2 there. And what I'm going to do now is test a 1 and test a 3, and when I do that, I get a negative and I get a positive, which means I have concave down, concavity down, and then I have concavity up, which means there could be an inflection point right here. So let me evaluate my function, my original function, at 2. But hang on, hold up, my original function at 2 has a vertical asymptote at 2. So this is undefined at that point, which means that no actual inflection points exist. No inflection points exist. Alrighty, let's sketch this thing. This is going to be a really interesting graph because we have that slant asymptote going on. It's going to be kind of a lot of fun to sketch out here. Okay, let's get our y-axis going. Let's get our x-axis going. Okay, and we're going to make our scale by 2s. So we're going to go 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, negative 6, and just keep making those marks out. Alright, let's take care of our asymptotes first. That is always a good first strategy to take care of. We know we have a vertical asymptote at 2, so let's throw that in there. I'm going to use a different color, make it look kind of pretty. Okay, vertical asymptote at x equals 2. I'm going to label this is x equals 2. And then we also have that other interesting slant asymptote at y equals x. Remember the line y equals x is just that perfectly diagonal line right through our graph. Has a slope of 1, so I'm going up 1 over 1 with this line. And I'm going through the origin. The line y equals x goes through the origin. And I'm going to label this line as y equals x. Label your asymptotes when you draw them. I'm also going to have my minimum and my maximum values that I found for my first derivative test. I know I have a maximum value at 0, negative 2. I'm going to label that point. And I know I have a minimum value at 4, 6. I'm going to go 4 and then up 6 should be about here. I'm going to label that point as well. Okay. Now, what's left to do is really just draw the rest of my graph following those rules. I know that I am concave up, or pardon me, I'm concave down in this interval here, and I know I have to kind of hug close to these asymptotes. So I know that my graph is going to do this. It's going to come out to this maximum value, and then it's going to drop back down and it's going to hug this asymptote. There we go. And over here, I know I'm going to be hugging my asymptote, and I'm going to come down to this minimum, and then I'm going to go back up, and I'm going to hug my slant asymptote as I come back up. And there we have it, the sketch of this curve. Pretty interesting stuff. Alright, let's do another example. Let's talk about a logistic function. And then I'll leave you alone. This will be a longer video. Sorry, but sometimes we gotta do that. Logistic function. Okay. And we're asked the question, analyze and sketch the graph of f of x equals 1 over 1 plus e to the negative x. Alright, this one's going to be kind of fun to do as well. Start off the same way every time. Let's talk about those intercepts. Okay. So, we have an x-intercept we set our y value to 0. So we're going to say 0 equals. And then we're going to say 1 over 1 plus e to the negative x. We would start to solve this by multiplying both sides of the equation by the denominator. But when I do that, I get the equation 0 equals 1. I know that's not true. I know this is a not equal to sign here. So in short, what we've arrived at is that there are no x-intercepts. Alrighty, that tells us a lot. Let's look at our y-intercepts. Remember, y-intercepts happen when we set x equal to 0 in our function. So we have 1 over 1 plus e to the negative, and then I just have 0 in there, so I'm just going to write 0, e to the 0. Remember that anything to the 0 power is just 1, so I really have 1 over 1 plus 1, or 1 over 2. And so I have a y-intercept at the coordinate 0, 1/2. Cool, cool. All right, let's talk about those asymptotes, those all-important asymptotes. Okay. And to do that, we're first going to talk about the fact that y equals 0 is a horizontal asymptote, and we'll discuss why in a second. But first of all, just write it out, horizontal asymptote, first of all, at y equals 0. And let's look at our original function to discuss why this is true. And then we'll talk about the degree and whatnot. So, what we've got going on with this function is the following thing. If we look at the limit of this function as x approaches negative infinity, right? What we've really got going on is a 1 over 1 plus 1 over e to the x, right? To the negative x just means like we have 1 over e to the x. So what we've got going on when we throw negative numbers in here, if I put a negative number in for x, that would make the e go back on top, and I would get really big numbers. If I threw like negative 100,000 in here, that would be the same as e to the positive 100,000, and then I would have a huge number on the bottom. But remember, when I have a huge number on the bottom of a fraction, it actually makes the number really small. So what I'm approaching, the y value I'm approaching when I throw big numbers in here, is 0. And the other direction, when I look at my limit as x approaches positive infinity for this same function, for 1 over 1 plus 1 over e to the x, right? If I throw big numbers in here where e isn't going to go back to the top because it's going to be a positive exponent, it's just going to stay there on the bottom, that's going to become a really tiny number. I'm going to have 1 over an increasingly larger number, which means this piece is going to get smaller and smaller and smaller until it kind of just goes away. And then what I'm left with is a 1 over 1. And I know that that will get me the number 1 eventually. That's what I'm going to approach as I throw in bigger and bigger numbers for x. So those are where my two horizontal asymptotes are happening. And we had to do a little bit more work there because this wasn't a straightforward, nice and easy rational function. So we had to look back at our limits for that. For vertical asymptotes, we can try and find one of those by setting the bottom equal to 0, right? That's what happens with vertical asymptotes, and the bottom equals 0. So we'll say 1 plus e to the negative x equals 0. And I get e to the negative x equals a negative 1. Interesting. And then I get natural log of both sides to cancel out that e. Natural log. Oh, something interesting is happening there. And I get negative x equals natural log of negative 1. And right away I know that there's something fishy going on. If you take a second and throw that into your calculator, you'll understand that this cannot be done. There isn't any exponent that you can create to make a negative number. You can make smaller numbers as exponents, but you can't make negatives. So this is actually undefined, which lets us know that there are none. There are no vertical asymptotes. Let's talk about symmetry. Really quickly again, so y-axis, make the x a negative, so I would get y equals 1 over 1 plus e to the regular x. And that is different. That's completely different. There's like not a little 1 over e to the x anymore. This is a like fundamentally different function. My x-axis, well, I have to make y negative this time, and I have 1 over 1 plus e to the negative x. And this isn't the same. I couldn't factor out a negative 1 at both sides and get an equivalent function, so this is no. My origin, let's try everything over again. Negative y, 1 over 1 plus e to the negative, positive x now. It's a positive x there. Okay. And again, fundamentally different. I don't have this going on anymore. It's just not the same. No. So I have no symmetry going on in my graph. And here's what we need to do next. Our first derivative. This is where things start to get kind of fun. We really get to tell a lot from our graph from the first and second derivative test. So this is personally my favorite part. We kind of make things a little bit interesting now. So first derivative, let me write out f of x one more time, so we kind of get that reminder of what we're working with. 1 over 1 plus e to the negative x. All right. I'm going to rewrite f of x right now as negative 1 times 1 plus e to the negative x to the negative 1. That is this isn't a negative out front. Excuse me. It's just this whole expression on the bottom to the power of negative 1. That's why it's at the bottom of fraction. Okay, moving on. Let's take the derivative of that. F prime of x, we'll take the derivative of 1 plus e to the negative x times negative 1. We can see this is kind of just begging to be derived using the chain rule. So we're going to use the chain rule. I'm going to take that power negative 1, I'm going to put it in front. And then I'm going to take the derivative of the inside. And remember, what I do there is I get negative e to the negative x, because the derivative of e to the negative x is itself kind of used by the chain rule. You kind of take the derivative of the outside, so you put that negative in front, and then you take the derivative of the inside, e to the negative x, and that is still just e to the negative x. So that's why I get the derivative of negative e to the negative x. When I multiply this negative e to the negative x by negative 1 out front, I get just regular e to the negative x times 1 plus e to the negative x. And I have, oh my goodness, I forgot a piece. Hang on. This should be to the negative 2. This should be to the negative 2 because I had to do negative 1 minus 2. My goodness, I almost forgot that. And now I am left with a positive e to the negative x all over 1 plus e to the negative x squared. And I know from before, like we just talked about, there is no exponent I can throw in here to make this 0 on top. And on the bottom, same thing. I know from when I just tried to find the vertical asymptote, I can't make this 0. So no critical numbers exist here. No critical numbers exist. Let's move on to the second derivative then. All right, f double prime of x means I'm taking the derivative, d dx, of e to the negative x all over 1 plus e to the negative x squared. I'm going to use the quotient rule this time. Lots of fun. I'm going to take low, which is 1 plus e to the negative x squared. I'm going to multiply it by the derivative of the top. Remember, the derivative of e to the negative x is just negative e to the negative x, minus high, which is e to the negative x, times derivative of the low. So I am going to have to use the chain rule there once more. I would take that 2 and I would put it out in front. And then I would have 1 plus e to the negative x on the inside. And 2 minus 1 would still be 1 right here. And then I multiply this piece by the derivative of the inside. The derivative of the inside is negative e to the negative x. Okay, and I have written out the whole numerator. And I say times the low squared. And if I square a square, I get 4. Alrighty. And here's where some really cool math starts to happen. So, what I actually get from right here, from 1 plus e to the negative x squared, is 1 plus e to the negative x times 1 plus e to the negative x. And when I multiply all of that out, I end up getting the trinomial e to the negative 2x plus 2e to the negative x plus 1. And so that's this piece right here. I actually have negative e to the negative x times that whole trinomial. E to the negative 2x plus 2e to the negative x plus 1 minus, and then I get to do some really fun stuff. Right here on the outsides, an e to the negative x times a negative e to the negative x is going to get me a negative e, and then I add the exponents. A negative 1 minus 1 is a negative 2x, so that's the outsides there. And then I say that's times this part distributed. The 2 distributed back, so 2 plus 2e to the negative x. And I have that all over 1 plus e to the negative x to the 4th. I know I got a lot of e's to negative x's here, but we'll get through it. All right. What we do now is we take these things and we distribute them. So we're going to take my negative e to the negative x and distribute it to all 3 terms in here. So what I'm going to get when I do the first term is a negative e, and then I'm going to add my exponents, right? A negative minus 2 is negative 3x. And again, I'm going to get a negative 2e, and then negative minus 1 is a negative 2x. And then times itself, so negative e to the negative x. That takes care of that portion there. And now I'm still going to hold on to my negative. I like to put that at the very end so I don't mix up any signs. I'm going to take this and I'm going to distribute it to both terms in here. And I'm going to get negative 2e to the negative 2x minus 2, and I'm going to have e, and I'm going to add these exponents together. Negative 2 minus 1 is a negative 3. And I have this all over 1 plus e to the negative x to the 4th. Okay, we're almost there. Negative e to the negative 3x minus 2e to the negative 2x minus e minus x, and now I'm going to change my signs, plus 2e to the negative 2x plus 2e to the negative 3x. All over 1 plus e to the negative x to the 4th. Okay. And now, so close. What we do is we cancel out the things that are the same, and we combine everything else. So, a 2 minus a 1 for the same power there is going to be 1e to the negative 3x. Those two cancel. And then I have this minus e to the negative x all over 1 plus e to the negative x to the 4th. Almost there. I have to factor out now. From the top, what I can do is I can factor out an e to the negative x. And here's what happens when I do that. I'm going to get on the inside for my first term an e to the negative 2x, because negative x minus 2x is negative 3. And then we're going to get minus 1 all over 1 plus e to the negative x to the 4th. And I'm going to do the rest on a separate page, but what I'd like to show you, or you know what, I think I'll just write it up here. what I'm hoping you see right now is how similar this piece right here is to this property of binomials. X squared minus 1, right? Which we know is actually x plus 1, x minus 1, right? So we're really close to that with this expression. It's just going to look a little bit different. And here's what I mean by different. We can say, I'm going to draw a little arrow, start the work back up here. E to the negative x outside e to the negative x plus 1 times e to the negative x minus 1 all over 1 plus e to the negative x to the 4th. And again, we got that just from that property of binomials. And now something really interesting happened. I can cross off one of these from the bottom and the top. And I'm left with, finally, my f double prime of x is e to the negative x outside e to the negative x minus 1 all over 1 plus e to the negative x to the 4th. Okay, let's use that. Again, my second derivative is e to the negative x outside e to the negative x minus 1 all over 1 plus e to the negative x to the 3rd now. Oh, I didn't make that correction back here. Make sure you do. This should be a 3, not a 4. Pardon me. Okay. Because we took one of them away. Now, let's identify any critical numbers that we might have in here. Okay. And here's what we're going to do and how we're going to figure that out. We've beaten kind of this one into the ground. We understand from our vertical asymptote conversation that I can't make the bottom of this 0. I wouldn't have any vertical asymptotes. That's not going to get me anywhere. I understand also that right here, this factor, this e to the negative x, I'm not going to get a 0 out of that. I'm not going to get a critical number from that because there's no thing I can throw in for x that would make me a 0. That just doesn't happen with exponents. I can get a small number, but I won't get 0. Here, in this factor, what I can do is get something to subtract 1 to make 0. And what I'm going to ask you to do is recall what power we can make anything this power and it creates 1. And I'm hoping you're thinking of the number 0. What I can do for this factor is if I throw in a 0 here for x, e to the 0 minus 1, I get 1 minus 1, I get 0. So I actually have a critical number where x equals 0. Cool stuff. Let's use that. Alright, there it is, 0, and I'm going to have a positive when I throw that into my second derivative, and I'm going to have a negative when I throw, oh pardon me, I guess I should have my test number. If I tested like a negative 1 and I tested a positive 1, and I put those into my second derivatives, I would get a positive and I would get a negative, which means I would go from concave up to concave down. I have a possible inflection point here, so let me evaluate my original function, my f, my original, at 0. And when I do that, I get 1/2. And so I have a point of inflection at 0, 1/2. All right, let's sketch this thing, and I'll leave you alone. So we've got kind of a shorter y-axis because we don't have a whole lot going on. We have two horizontal asymptotes. Remember, we have one at y equals 0. So it's going to be important for us to show, kind of extend out in a different color or something to remind yourself that, yeah, this is the x-axis, but it's also our vertical asymptote, y equals 0. And give yourself another vertical asymptote. Let's call this 1/2, and let's call this 1. Give yourself that other vertical asymptote, or I'm sorry, I keep saying vertical, horizontal asymptote at 1. Those were our two horizontal asymptotes. Alrighty, And we don't have a lot going on because we didn't even get to have the first derivative tell us anything. But we do know some things. We know that we have a point of inflection at 0, 1/2, so I'm going to label that. And we know that we were concave up, and then we were concave down, which means I'm going to hug this horizontal asymptote here. I'm going to hug it, going to hug it, going to hug it. I'm going to go up to meet my point of inflection, and then I'm going to hug my top horizontal asymptote of y equals 1. And that's kind of what my graph is going to be doing. Okay, thanks for watching. We'll see you in class tomorrow.